am Kalai Selvi, Assistant Professor of Chemistry, JJ College of Arts and Science, Pulkotai. Now we have discussed about infrared spectroscopy. What is meant by spectroscopy? Spectroscopy is the study of the absorption and emission of light and other radiation by matter. In infrared spectroscopy, also the study of absorption and emission of light. So now we have discussed about the brief infrared spectroscopy. So the IR spectroscopy is the study of interaction between infrared radiations and matter. Infrared radiations refer broadly to that part of electromagnetic spectrum between visible and microwave region. So the electromagnetic spectrum means the electromagnetic radiations are arranged in the increasing frequency or decreasing wavelength. That is called the electromagnetic spectrum. Okay, so this infrared spectroscopy arranged between visible and microwave region. So this is the principle of IR spectroscopy. So it is related to a vibrational and a rotational energy of a molecule. So when the frequency of IR radiation is equal to the natural frequency of vibration, the molecule absorbs IR radiation. Absorption of IR radiation causes an excitation of molecule from a lower to the higher vibrational level. Each vibrational level is associated with a number of closely placed rotational level. So this IR spectroscopy is called vibrational rotational spectroscopy. All the bonds in a molecule are not capable of absorbing IR energy, but those bonds which are accompanied by a change in dipole moment will absorb the IR radiation. So this is a very much a condition in IR spectroscopy. So the transitions which are not accompanied by a change in dipole moment of the molecule are not directly observed and are considered as IR inactive. In IR spectroscopy, the changes in the vibrational energy depends upon the three factors. One is the mass of the atom present in a molecule, second one is strength of the bonds, and third one is arrangement of atoms within the molecule. So this is a theory of IR spectroscopy. When a molecule absorbs IR radiation with a frequency less than 100 cm minus 1, molecular rotation takes place, and if a molecule absorbs more energetic radiation in the region of 10 power 4 to 10 power 2 centimeter inverse, from this region the molecule vibration takes place. A single vibrational change is accompanied by a large number of rotational energy changes, and thus the vibrational spectra appear as vibrational rotational bands. So this is a fact of absorbed radiation. So there are three main processes by which a molecule can absorb radiation. Each of these routes involve an increase of energy which is proportional to the light absorbed. The first route is it occurs when absorption of radiation leads to a higher rotational energy level in a rotational transition. The second occurs when absorption of radiation leads to a higher vibrational energy level in a vibrational transition. And then third occurs when absorption of radiation leads to a higher electronic energy level in its electronic transitions. So this is an energy level diagram. So when a molecule absorbs V1 radiation, V1 absorb of amount of radiation, it goes to V0 to V1 or V0 to V2 or V0 to V3. So this is a simple energy level diagram. Two criteria must be satisfied by a molecule for the absorption of IR radiation. The molecule should possess vibrational and rotational frequency. The molecule must give rise to asymmetrical charge distribution. Three main type of absorption bands occur in IR spectra. One is the fundamental, overtone and conventional. So this is a Fermi resonance. Interactions which occur between fundamental and overtone are called Fermi resonance. Overtone means the vibrational level transition takes place. For example, a V0 level excited to V2 level or V3 level, that is called overtone. Okay, so this is called Fermi resonance, and this phenomenon can be observed whenever two fundamental and overtone bands have nearly the same energy. Here, molecule transfer its energy from fundamental to overtone and back again, and so that the each level become partially fundamental or partially overtone in character. As a result, two strong bands are observed in the spectrum instead of the expected strong and weak bands. For example, we will take carbon dioxide. It normally shows a fundamental band at 1337 centimeter inverse and overtone at 1334.6 centimeter inverse. But due to the effect of Fermi resonance, the first band shifted towards a higher frequency and give rise to two bands. One is 1285.5 centimeter inverse and 1388.3 centimeter inverse. So this is very important in IR spectroscopy fingerprint region. In IR spectroscopy, the region below 1500 centimeter inverse is called the fingerprint region. Here the number of bending vibrations are usually more than the number of stretching vibrations. So in this region, small difference in the structure and the constitution of a molecule result significant changes in the absorption bands. Many compounds show unique absorption bands in this region, and which is very useful for the identification of the compound. So this is an example for fingerprint region. So this fingerprint region can be subdivided into three regions. One is 1500 to 1300, 350. Second one is 1350 to 1000, and third one is below 1000 centimeter inverse. So the first region shows the tertiary butyl group, the second one due to CO groups, and the third one groups cis trans alkenes. So in IR spectroscopy, the vibrations are classified into two types. One is a stretching vibration, another one is a bending vibration. The stretching vibration is divided in two types. One is symmetric, same direction. Another one is asymmetric, the vibrations are in different directions. The bending vibrations are also classified into four types: scissoring, rocking, wagging and twisting. So this figure explains the types of vibrations, and these are the factors influencing absorption. The first one is symmetry. Symmetry compounds do not possess a dipole moment, so they are IR active. And the second one is coupling. There are so many factors which cause coupled vibration in IR, and it will influence the intensity and shape of the absorption bands. Third one is Fermi resonance. Fermi resonance result in an unexpected shift in energy and intensity of the bands. For example, overtone of CH deformation mode at 1400 centimeter inverse is always in Fermi resonance with the stretch of the same band at 2800 centimeter inverse. The another factor is the hydrogen bonding. It can change the shape and the position of IR bands, because the hydrogen bonding presence of two types. One is intermolecular, another one is intramolecular. The intermolecular gives a broad band, then the intramolecular gives a short bands. And next factor is electronic effect. The electronic effect means such as inductive or mesomeric and field effect may cause shift in absorption bands due to the change in absorption frequency. And next factor is a bond angle. A difference in bond angle can also lead to the changes in absorption bands. So these are the examples. The first one example is cyclopropanone. It gives 1815 centimeter inverse, and second one is cyclobutanone. It gives 1780. So the bond angle is decreased. Okay. So these are the sampling techniques. So samples of the same substance shows shift in absorption bands as we pass from solid to gases, and hence the samples of different phases have to be treated differently in IR spectroscopy. If the sampling of solids, the solids run in solution, we have to use a Mull technique, pressed pellet technique or solid films. Thank you.